Just use metal plate, metal plate, metal plate. Now again, Walker, these are two metal plates. They're three-dimensional plates. You got it?
Okay.
All right.
The plates are fine because I can imagine that.
The more charge, the potential difference. The more the charge, the more the potential difference. So the formula is V equals Q over C, right? Now, we're going to try to figure out how the capacitance formula, C equals Q over V, we're going to try to use the ideas from what we learned last chapter to figure out what the capacitance formula between two metal plates would be. Ooh, that sounds like fun.
But what?
Yeah, what? So, how would you find if I had one metal plate sitting here in space and I had a charge spread around the plate equally, because that's what happens on metal plates? How would I find the electric field a distance from it? Oh, it's still coming back.
No.
Oh, yeah. I use Gauss, whatever. We would go, Gauss's law says the closed integral of E dot dA is equal to charge enclosed over E naught. And what shape would I pick?
Cylinder.
A cylinder with the end caps on there. So the end caps would be, so this would be E. I have two areas it can punch through, right? So 2 pi r squareds equals a charge enclosed. Now, there's a problem here because I said there's a charge on the surface, right? So I'm going to say, well, all right, hold on. Charge per unit area is hat boy. Right? And so hat boy times the area of this thing, which would be pi r squareds, over E naught would be my charge enclosed over E naught. We recognize this because an old saw that our pi r squareds disappear. And we get E equals hat boy over E naught. Over 2 E naught, right. Thank you.
That would be for one plate.
That would be for one plate. So if I have a second charged plate right down here, and it's charged the exact same way, and I draw a shape to the same spot, what would be the electric field it would create? It would be hat boy over 2 E naught. And so the total electric field would be what?
Hat
boy over E naught. That's electric field. How does that help us? Potential difference between two metal plates. How do I find what the potential difference is?
Integral.
We'll do it the hard way. Good. We'll do the integral of the electric field with respect to distance is equal to potential difference, right? Now, we know it's a constant electric field between those two plates, right? Because there's no R in my formula. It's always going to be the same. So I'm going to go ahead and plug this in. I go integral from... Now, where would I start? I would start from one plate to get to another plate to figure out what the voltage between the two plates is, wouldn't I? Which is what we're talking about when we talk about capacitor. So that would be from, say, 0 to distance D. Let's call that distance D, shall we? Our constant electric field, hat boy over E naught, dr equals V. Now that's a constant, right?
What's hat boy?
The whole thing, right? Yeah. So I can pull out hat boy and E naught, hat boy and over E naught, and I get the integral from 0 to D of dr equals V. Well, there's nothing in there, right? So that makes it an R, right? Hat boy over E naught times R from 0 to D. Equals my voltage. And I get hat boy D over E naught is my voltage.
Oh, this is just a proof.
This is a proof, yes. Now that I have the voltage, you grasp that fast. So now I have a voltage, I can put it down over here, right? I can put that in the where capacitance is.
Sure.
So I would get capacitance is equal to, now I'm going to flip and multiply in one step. Is that okay with you? I got Q over hat boy D E naught.
See, okay, now what is that distance? Is that like a radius or something?
That would be the distance between the two plates. I'm traveling the electric field this distance to go figure out the voltage between the two. Right? Now, last but not least, I don't like hat boy. What was hat boy? Charge per unit area. So I'm going to write that out as charge per unit area. I got Q over E naught equals Q over area D. Flip and the Q's cancel out. Flip and multiply. I get A E naught over D is equal to my capacitance. And that is the capacitance of the plates. The area of the plates divided by the distance times this arbitrary constant E naught is the capacitance of a capacitor. Now that we have the formula, we recognize it's almost like that on your formula sheet. I need to add one more thing. One more thing. Some crazy person in the past thought, well, what if instead of leaving this as an airspace in between the two, what if I throw some goo in there? And specifically, I throw goo in there that spins. What? When I put a negative down here, these things go, oh, the positive goes down here, the negative goes up there, which would create an even greater electric field through the middle here, which would in turn create a greater desire for electrons to flee that surface. If I did that, I'm putting goo in there. The goo is called a dielectric because it spins. And theoretically in chemistry, you learned what dielectric is. Don't answer that question. Theoretically, what you do. Okay? And so the better the goo works, the better the capacitance of the capacitor, right? Because you can store more charge with less voltage, right? Because more will flee. And so we're simply going to add to this formula a K, because that makes sense for dielectric constant, A E naught over D, and that is the capacitance of any capacitor in existence. That's two parallel plates. Yes?
K, the K constant K, the K.
It's a K constant. That K is going to be the dielectric. I don't even know how to spell dielectric. I will look this up. It's on here. Goo. G-O-O. That one I got. Because it's a real word as opposed to dielectric, which is really not. Dielectric.
You know how to spell electric, right?
Yes. I wanted to make it dielectric, and I was struggling with the A and E, or is it an A-E together? It says dielectric, so my bad.
Okay, wait.
Yes.
This spinning goo. I don't know. Is it?
It looks like you put a piece of rubber in there.
Oh, well,
It can't allow electrons to flow because that would be what? That would be conductor, and that would mean the capacitor would stop working. But if you put goo in there where it's polar, it's got a plus and a minus sign. When I start piling minuses on this plate, what happens to that goo? It flips over.
Oh, okay.
It flips over, it becomes plus minus because it can't travel and it can't transfer charge. So it flips over. When that happens, these things go, oh, there's positives right there. And so more electrons can be here. Right? And over here, more positives can pile up because they're closer to negative.
Are you doing this in real life?
Yes.
Why?
Because they want capacitors to work with more capacitance without making really big plates, right? Because the other way to make it is to make a big area plate. Right? The bigger the area of the plates, the more capacitance you have. So you have two options. You can make big plates inside of your computer, or you can put goo in between the plates and shrink down these things. The goo, there's a list of goo down there. Good question. Here's a list of goo. Sometimes they put vacuum in there. Sometimes they put Bakelite. Sometimes they put Pyrex glass. Sometimes they put Teflon in there. Sometimes they put paper in there. Sometimes they put water. No, they never put water in there, but okay, whatever. We'll pretend like they do. So they put fused quartz in there, polystyrene. The neoprene rubber goes in there. Strontium, you can see which one they really put in there. Strontium, titanate.
That's what they actually use?
Yeah, that's what they use because it gives you 233.
That's not rubber, that sounds like metal.
It does sound like metal, but it's actually resistant, so it doesn't actually, the current can't flow through it. Okay. All right, so that's the list. So, example, capacitor plates arrayed so they're 0.00010 apart, filled with air. What would be the area of the plates necessary to create a 2 pico, that's times 10 to the negative 12, farad capacitor?
Oh, the K isn't. Oh, I thought the K was